Hello, can you guys hear? Okay, cool. So I titled it this, but last week we had a slightly different title. I think it's a data flow or something, which might be what you see on the brochure. It's the same talk. So again, my name is Hidenori Shinohara. I'm a software engineer on the core team, and then today I wanted to talk about the TPS and transaction broadcasting, and then validation through simulations. So TPS, I think many of you are probably familiar with what it is, especially after the previous talk, but it's the transactions per second. So it's the number of transactions that the network is capable of processing every second. And it is a very important metric for cryptocurrencies, or not just cryptocurrencies, it's actually probably very important for most payments network, frankly speaking. And one thing I do want to mention is that the currently installed network is not limited by the TPS, as in the network usage. It's just fine. People can use the network as is. But having a higher TPS simply aligns with Stellar's ultimate mission, which is to operate at the scale of global payments network. So we're going to talk about how one of the projects that we have that's improving the TPS, and then that's related to transaction broadcasting. So the agenda. So first we're going to talk about what transaction broadcasting is. And next we're going to talk about why transaction broadcasting affects the TPS. Because we're going to talk about improving transaction broadcasting. But we're not going to improve transaction broadcasting for the sake of improving transaction broadcasting. It's going to be for improving the TPS. So we're going to see the connection. That's the second part. And next we're going to talk about how we're going to improve transaction broadcasting and hence improving the TPS. And then finally, we're going to talk about how we validated it and then tested the new design of transaction broadcasting using simulations. So what is transaction broadcasting? So it's relatively simple, but it's just the nodes in the network telling each other about transactions. There are a couple different names for that. So you might have heard of terms like transaction flooding or propagation. Some lesser common terms might be like dissemination. If you look at the Stellar core code base long enough, you might see terms like overlay. I've also heard of the term multicasting, if that makes sense. But those terms relatively pretty much describe the same concept. It's that the nodes in the network have to tell each other about transactions, and then that's what I call by transaction broadcasting here. And then one thing I do want to clarify is that the term broadcasting has this connotation that there's this one organization that's like broadcasting for everyone else. But in this context, it's that the nodes in the network are broadcasting with each other. They're telling each other about transactions. So now that we have the what, we're going to move on to the why. So why do we care about transaction broadcasting? So there are a couple of basic principles in cryptocurrencies that generally apply to most cryptocurrencies, and then they kind of answer the question as to why transaction broadcasting is related to the TPS. So the first principle is that, generally speaking, nodes have to know about all transactions because of ledger history. And as I mentioned earlier, in cryptocurrencies, there isn't like one centralized organization that's announcing transactions for everybody. So the nodes in the network have to tell each other about all transactions all the time. And then these two principles kind of lead to the third one, but the nodes in the network can't process more transactions than they receive, because if they don't know the transactions, they can't close a ledger with those transactions. So because of these reasons, transaction broadcasting rate is a limiting factor of the TPS. And because of this, we wanted to improve the TPS, and for that we decided that we're going to look at how transactions are being broadcast throughout the network. Like how transactions flow through the network. And we noticed that there was one area that seems a little inefficient, and then we decided to try to improve it. So we're going to look at what broadcasting looks like in real life, and then we're going to see that inefficiency. So let's say that the Stellar network has 5 nodes. In reality, we have a lot more than 5, but let's say that we have 5. And then this node on the left, the square with the arrow, let's say that that's a transaction. Then this node on the left has this transaction that wants to be included in the next ledger. So let's say that they start broadcasting, which is great, and then these two other nodes receive this transaction. And so far so good. This is a great transaction broadcasting going on there. And this is where things get a little interesting. These two nodes, so one in Europe and then one in South America, both decide that they're going to send this transaction to this node in the middle in Africa. So how many times did this node in the middle, the node in Africa, hear this transaction? Twice, yes. So that's more than one. It's a big deal. It's not clear, but it's twice, so that's something to notice. So let's say that this node, again, sends this transaction to this node in Asia, which is great because now everyone in this network has heard of this transaction, which was the goal of transaction broadcasting. But then the nodes might keep going. And then maybe the first node decides to send it again to some other node. So how many times did this node in the middle? Yes, 3. So you might know where this is going, but the node on the right sends this transaction to this node in the middle. So how many times in total? 4, yes. So you can see how this is getting a little repetitive and unnecessary because this node in the middle heard this transaction for the first time, like a couple slides ago, but they keep hearing the same transaction. And in this example, this node only heard it 4 times, only 4 times. But in reality, we recommend that every node in the Style network be connected to at least 8 peers for liveness purposes. And some nodes are connected to more than 8 nodes. So let's say that you're connected to like 30 peers. Then you might potentially hear the same thing up to 30 times. And then that's really unnecessary because every incoming transaction leads to some sort of computational power usage. Like to receive the data, you need to use some bandwidth. To read the data, you need to some CPU, and then to remember that you heard that data, you need some memory. So for those reasons, we decided that this is kind of inefficient and unnecessary. And we decided that we wanted to come up with some strategy to fix this. And this new strategy that we came up with, we call it Polo. And then the main idea is that you ask before you send. And what does that mean? So let's say that node 1 wants to send node 2 a certain transaction. Then instead of sending the transaction itself, node 1 will send this question. Hey, do you have this transaction? And then when it sends that transaction, it doesn't send the transaction because they'd be a little repetitive. So instead of the transaction, we send a hash of the transaction. And if you don't want to hash it, it's kind of like a short summary or identifier of the transaction. So without having the transaction, you're able to tell what that transaction is, or you can compare it with other transactions. And once you receive this question, you check if you know that transaction. And if you do, that's great, you're done. There's nothing more to be done. But if you don't, you will send this request. Please send me this transaction. I don't have it. And only if you get that request, you will send the actual transaction. So this is what I meant by ask before you send, because you ask if the other person has the transaction before you send the transaction. And you might have noticed that we're trying to optimize this communication channel, but we're introducing this many messages that we're doing this like back and forth, which might not seem like very efficient in the beginning, but the hash or the short summary that we send is significantly smaller than the actual transaction. So there is this huge save. We can save the bandwidth so much, and we figured that that trade-off would be worth it. And we're going to revisit that a little bit later. But the idea was that because we can remove duplicates, we're okay with this extra back and forth. But we're going to see how this Polo can remove duplicates in the previous example. So earlier we had these 5 nodes in the network, and a couple of nodes had heard of this transaction. And then after this, the 2 nodes in the middle sent the same transaction to this node in Africa. But with Polo, instead of sending the transaction, which can be big in the byte size, they will send a hash, and they'll ask, hey, do you know this transaction? I have this, but I'm not sure if you do. And because this node in the middle doesn't have this transaction, it'll request it. Please send me this transaction, I don't have it. And once that request is received, the node in South America will send this transaction to the node in the middle. Then this node in the middle will only receive this transaction once instead of like 4 times like we did earlier. So we thought that was a really cool idea that can remove duplicates in traffic. But we have to make sure that it works. And then that's why we have this new slide titled How to Validate Polo. So when we came up with this idea on Polo, we were really excited. We thought it was a really good idea, but there were so many questions to it. And then the first question is, does this even work? And it sounds like it works, right? I mean, you send this, hash, you get a request, and you send a transaction. What could go wrong? So sounds like it works. It's obviously not good enough for a financial network. So we had to have some sort of proof or something a lot more substantial than that. And then the second part, does this improve the TPS? So this question is actually very interesting because so Polo obviously helps remove duplicates or reduce duplicates at least. But as I mentioned earlier, the ultimate goal we had was to improve the TPS. So if removing duplicates doesn't lead to higher TPS, then the goal of the project is a little bit unclear. And that was kind of the whole point of this project. Then in the beginning, I was like, if we can remove duplicates, how could it not improve the TPS? Obviously, it's going to be more efficient. So it turns out it's not that simple because of the trade-off that I mentioned earlier, that we would remove duplicates, we would save some bandwidth, but we would introduce some extra round trip. So it's not that obvious that this trade-off is a good trade-off, that this change is going to improve the TPS. So that's something that we have to answer. And then to answer these questions, there were a lot more questions than this, but to answer these questions, there were many challenges in validation. So the reason why validating these things is very difficult is because there's so many factors when it comes to transaction broadcasting. So if you're thinking about transaction broadcasting, you obviously want to know the number of nodes that are broadcasting things, and then how those nodes are broadcasting things to each other, as in what peers are connected to what other peers. So you definitely want to know that for transaction broadcasting. And then again, for transaction broadcasting, you obviously want to know the number of transactions that are going on there. So you want to know about the transaction rate. But the transaction rate is not steady. It keeps going up and down because people sometimes use it more, sometimes use it less. So there are spikes in the transaction rate. So there are so many variables when it comes to transaction broadcasting, to the point that we couldn't just take a piece of paper and a pencil and improve it on paper. We obviously had to think a lot to understand the implication, but at the same time, we just kind of had to see how things work in reality, or at least something that looks like a reality. And the second point, I can't just test in the real network, it's very obvious, but we couldn't just write code and then throw it in the public and then see how it works. And that's obviously not an option. So for those reasons, we decided that we're going to do some simulations to basically simulate the network. And saying that is relatively easy, but it's actually very complicated because the Stellar network has hundreds of nodes. And then let's say I don't know, one way might be to just actually find where those nodes are in the real world, and then find a computer right next to it, and then start a node in each of those computers, and then connect those. And then obviously that doesn't work. That's just not realistic for many reasons. So we have to come up with some sort of clever setup to simulate the network without having hundreds of computers across the world running something similar to the actual network. So the simulation setup, it's called a supercluster project. It's in the public repository. And then the scope of the supercluster project is very, very big, and it goes beyond the simulations that we're going to cover in this talk. But as part of the supercluster project, we made a couple simulations that help us validate this new design of Polo. And as I mentioned earlier, we couldn't reproduce the actual network as is for many, many reasons. So we had to think about what aspects of the real network we care about. And then the first thing that we decided was network structure. We wanted to examine the real network and understand the network structure so that we can reproduce it. So network structure, I mean the number of nodes, what peers are connected to what other peers, stuff like that. And network delay, this is a very interesting one that I was not aware of in the beginning. But as I mentioned, the Stellar network has nodes across the world, like everywhere in the world. And then that's a good thing for decentralized network. But at the same time, if data is traveling from one continent to another, to yet another continent, each hop could be like a few hundred milliseconds or whatnot, and then they could add up, especially if you're closing a ledger every 5 seconds. So that's something we had to think about, but we couldn't rent, again, 500 computers around the world. That was just not a very viable approach. So what we did was to understand the network delay by looking at where each node is located, taking the geolocation of each data center, and they calculated the geographical distance between any pair of nodes that are connected to each other. And then using the distance and the speed of light to make some sort of educated guess on what the network delay might be between those two nodes. So obviously that's not a perfect approach, but that gave us a really good idea on how network delays might affect how transactions are being broadcast throughout the network. And then lastly, transaction rates and sizes. We obviously wanted to know how many transactions are in, let's say, each ledger to understand how transaction broadcasting works. And then this was actually pretty easy to check because all transactions that ever happened in the Cell network are public, in ledger. So you can look at any past ledger history and then understand the number of transactions in each ledger. So once we had these types of information that we wanted to reproduce from the real network, we went on about it using different technologies. So that's the second part of the slide. So we used Docker and AWS clusters to run different nodes in a small number of computers. And then we used Kubernetes to orchestrate them. And then once we had the network up and running, we had those nodes create mock transactions that resemble the real transaction based on the patterns that we saw earlier when we were examining the network. And then by using this strategy, we were able to capture interesting behaviors without having to replicate the real network. As in, we didn't have to have hundreds of computers across the world. We just had to have, I don't remember the exact number, but like 5 to 10 computers to simulate a network with like 50, like 100, or even more nodes in a realistic way. So this helped us simulate the network and then gave us a lot of idea on this new design. But simulations aren't the reality, obviously. So there were a couple pros and cons, and we're going to go over that. So the first point that was good is that fewer machines are necessary. Again, we don't want to rent 500 computers around the world. We could only just we could do a simulation with like 5 to 10 computers, which was like much nicer in terms of just efficiency, and also it was just more cost effective. But there was an issue that corresponds to it, which is that each node has less CPU. So in the real network, most node operators are not running like say like 50 nodes per computer. But in the simulation, we were doing that. So that means each node has much less computing power than most nodes in the network, if not all. So that meant that whatever simulation that we were running, we estimated that it would probably underperform the actual reality. And then the second item on the pros is we were able to tell a big picture relatively quickly. So whenever we have some sort of discussion on a certain aspect of Polo, we were able to write code and then compile it and then run the image, run the simulation. And then in a matter of a couple hours, we were able to tell if this new change in Polo will improve the TPS or not. And that helped us make good decisions with more confidence relatively quickly, because that gave us a lot of early feedback. However, corresponding to that, there was an issue, which is that absolute numbers were likely to be inaccurate. As in, if, say, in the simulation, the network had, I don't know, the TPS went up by 5, then we didn't expect that in the real network it would go up by 5. we just assumed that it would probably go up by a little, but we didn't really look at the absolute numbers too carefully. We looked at relative numbers, as in like how much it went up, did it even go up, but we didn't look at the absolute numbers. So based on these pros and cons, we ran a lot of simulations. So the first one that we have was realistic network. So this is the simulation where all the properties that we observed in the real network, we tried to reproduce as many of those as possible. So this is our version of like the real network in the simulation. So this helped us understand, say like the CPU usage of each node or the memory usage of each node. And it's not going to be perfect, but it gave us a lot of good ideas and then help us understand how things are in the real network. And the second one was limit testing. So this is a cool one because this is where we have a simulation up and running in the cluster, and then that's when we crank the TPS. So we continue to throw more and more transactions to the network until the network breaks. So this helped us understand what the maximum possible TPS was for the specific change on the network that we had. And then lastly, we have a lot of different network structures. So as you know, Style Network is an open membership network. So that means anybody can join the network anytime they want, and anybody can leave the network whenever they want. So the network structure continues to change. The number of nodes continues to change. So we couldn't just take one snapshot of the pubnet and then just be done with it. We have to think about what types of topologies that could appear in the future, for instance. So we tried to think of many different possibilities and scenarios, and then try to understand what would happen in those situations. So as you can tell, there were many simulations that we ran, and I want to highlight some number from those. So the specific number that I want to highlight is from the combination of 1 and 2. So we had a realistic network up and running in the cluster, and then we tried to push the TPS as far as we can to understand the maximum TPS that we might be able to achieve. So for latest stable release, 326, so this was before Polo. So without Polo, in the simulation we were able to perform 326 transactions per second, which I think is a really good number already. But once we implemented Polo, we were able to get 563 TPS, which was a significant increase from the previous version. So obviously, Polo seems to help with the TPS quite a bit. There are a lot of caveats. Again, each node in the simulation has a lot less computing power. So there's a good chance that we might be able to achieve a higher number in the pubnet with Polo. However, again, there are so many differences between the simulation and the reality. So we can't just take this number and apply it to the real network and expect that we'll see this number in the pubnet right away. But this simulation is a strong indication that this new change in transaction broadcasting would help the TPS significantly. So finally, to recap the talk, lessons that we learned from this talk, this project is that Polo optimizes transaction broadcasting by removing duplicates. And then by removing duplicates, we were able to improve the TPS. And because we ran so many simulations, we were able to get a lot of early feedback on a new design idea that we had. And then that helped us make good decisions very quickly with a lot of confidence. And then finally, I guess this is not a lesson, but the image with Polo implemented is publicly available right now. So any node operator who is curious about this new feature is able to turn it on through their config file. Thank you for your time. Thank you for listening to the whole thing. If you have any questions, I'm here to answer.
Hi, thank you very much for the lovely talk. I really enjoyed it. There's a lot packed into that talk. So can I just mention a few questions? And you
Yes, for sure.
So first of all, it would be interesting to know how many repeats, duplicates you saved. You gave the TPS figure, but you didn't give figures for how many duplicates may have been avoided. Also, there's the component of what you did with your simulation framework, but implicit in your talk is how important simulations are for making design decisions in this space. And I wonder how generally useful your framework might be within Stella, or just as a generic blockchain testing framework. And that makes me wonder how many other things there might be out there that do a similar job. And I'll stop asking questions then, thank you.
So the first one, which one was the first?
How did you measure how many duplicates were saved?
We don't have access to metrics from third-party nodes, like us, and like non-Stellar nodes that are running in the pubnet.
On your simulation, you ran
in the simulation, I think from some nodes, the incoming traffic was like up to like 90% duplicates. Yeah, and then if Polo works perfectly, then there is no duplicate. So yeah.
And the other comment is, you appear to have built a simulation,
yes,
a twin of Stella, and implicit in your talk, so implicit you said, it's really important to have this thing to test ideas.
Yeah.
Is this something that could be packaged up and provided as, maybe you've already done this, if you packaged this up and provided it generally for testing ideas in Stella, or more generally for testing ideas in blockchains?
Yes, I have heard that like a lot of cryptocurrencies do some sort of simulations. I'm not super familiar with exactly how they do it. As for making it publicly available, the code base for this simulation is publicly available. However, there's a lot of like a nuance, like detail, like configs that you need to do to make it work with your own cluster. So I don't think it's, could be wrong, but as far as I can tell, it's not in a place where you can just clone the repository and in 5 minutes you can run the simulation.
Thank you.
So Stella's mission, which was reminded at the beginning, was to have a TPS that was scaled to a global payments system. What is that benchmark, if you're happy to share?
Tom might be a better person to answer that question, Coach.
Yeah, in the industry, people look at like Visa as like a scale, which is usually this quoted around 24 to 27,000 transactions per second. But the Visa network is actually very short. It's unrealistic to expect it to be short. Other than reaching these numbers. So it's, yeah, in short, it's hard to find.
And a final follow-up question then, is sharding in the roadmap?
Sharding is not currently in the roadmap for Stella. We're really focused on making the base layer as basically as scalable as possible. We do have efforts around meeting channels with the Starlight project. We did when I think of the various on-chain instructions for achieving scalability. Sort of what we'll talk about tomorrow also enables various roll-up designs that are implemented on the current protocol because it doesn't have the type of general programmability that allows you to spread it.
Thank you. Cool, I think that's it. Thank you so much.